curveballs, a fascinating thing done by footballers or baseball players to create unexpected paths of the ball to outplay their opponents. How does that work? This is the effect that we are investigating in our project, the Magnus effect, and I'll explain to you right now what that means. Here's a projectile spinning in clockwise direction. So let's say it travels here. So air flows against the ball like that. From Bernoulli's principle, which states the pressure on one side N is sum to some multiples of the kinetic energy, let's say, is equal to a constant. So that's why we know when this side of the ball flows with the airflow, so it speeds up the airflow, and vice versa, this side slows down the airflow. So that's why the pressure increases in this side and it drops on the other side. And pressure is also a measure of force. That's why we get the Magnus force pointing upwards due to the pressure difference. In our project, we'll investigate how the spin and also its axis affects the magnitude of the Magnus force, and also, most importantly, its direction, to investigate the physics behind the curveball.
In this project, we are investigating the Magnus effect on a ping pong ball, as aerodynamic effects are less complicated on spheres. Before proceeding to the experimental part, Jack will explain to you how we built our custom ping pong launcher from scratch under limited budget.
Okay, so here's the engineering part of our project, and basically we have built this ball launcher from scratch. In the past few weeks, Connor and I built 5 different models of the ball launcher from more than 20 hours. In the first few models, we face a lot of limitation, and for example, we use a lot of glue and super glue which are not robust and it cannot be adjusted. Therefore, we input a lot of new tools and equipment to make everything more robust and make it adjustable. For example, here is the first model. The idea comes from that when the wheels are moving, it will accelerate the ball. When applying different voltage to the wheels, it can apply the torque to the ball and spin it out. In our final project, the Gen Sigma, we can we use a lot of new equipment. For example, we have the translation stage, which can adjust the distance between the two wheels, and we are using a better motor. We can accelerate up to 10,000 RPM. In order to sustain the high RPM, we have the better wheels that we made from the 3D printed carbon fiber, and it is wrapped with the professional ping pong ball racket sponge. In order to make everything more robust, we even have a lot of just supporting bars like this, so everything is fixed with each other. We also have the tube and rail guidance, which can make sure that everything is consistent, like this. Also, we have used a lot of gluing to fix everything together to make it more robust. In terms of the adjustability, we can adjust a lot of things. For example, if you want to adjust the polarized angle to apply not a horizontal spin to it, we can change this stand and clap. If you want to change the projectile angle, we can change the height of this clap. So we can change the projectile angle. If you want to change the horizontal angle, we can simply move the table. So we try to make sure that everything is more adjustable so we can take more data sets.
After finalizing the launcher, we are finally able to carry on and do experiments. I'll hand the time to Asim to talk about our experimental setup as well as the results.
We set up a blackboard for the ball to hit. This was 75 centimeters away from where you'd expect the ball to reach after traveling 5 meters forwards in the case where there is no curvature on the ball. We placed one camera above the ball at the start of its trajectory, which allowed us to track frame by frame in our slow motion recording in order to obtain an estimate for its initial velocity. Another camera was facing the blackboard to track whether or not the ball hit the board or not, thus determining whether this launch was acceptable or not. Another benefit of this was we'd now be able to obtain the full trajectory of the ball up until it hits the board. The final camera was at the end of the trajectory in order to determine the final spin rate and thus to infer what the initial spin rate was.
To ensure fair comparison, we also applied the same voltage on the two motors by connecting them in parallel to the same power supply, so they spin at the same rate, in order to show that when spin is not induced on a ball, it travels nice and straight. Of course, to quantify our experimental results, a simulation was also made beforehand. I'll let Lorenzo explain how he developed the physical model and apply it to data analysis.
The simulation was used in order to predict the path we think a spinning ball would take, based on the standard Magnus force equation. It starts by collecting the initial parameters of a ping pong ball as it exits our launcher, such as the initial speed, initial spin, launcher height, and launch angle. These inputs are then run through a set of equations used to model the Magnus effect. Projectile motion, as well as the drag and spin decay caused by the friction between the ball's surface and the air. Firstly, the simulation will solve the time of flight of the ball before it hits the ground, and then break up this overall time into many small intervals. At each time step, it applies the equations and solves for the forces on the ball, which in turn gives us the acceleration, velocity, and distance travelled during that short time. This method is repeated through all the individual time steps, whilst accounting for the drag and spin decay. Once completed, all these time steps are then put together to form the full predicted path. A few key issues were encountered during the coding process of our simulation. One such problem was in the calculation of the Magnus force. One of the terms used in the calculation involved a term in which you divided by the velocity. Therefore, at low velocities, the force would then blow up, creating unrealistic trajectories. Furthermore, we had an issue of the lift coefficient. Now, normally, the lift coefficient is determined experimentally using a wind tunnel. Unfortunately, we didn't have access to one, so we had to find a way of estimating it since there is no universal formula for it. After some research, we found an empirical formula where the lift coefficient is proportional to the spin ratio, where the constant of proportionality for a sphere is 1.6. However, this solution caused another problem in the code, as at high spins we would run into unphysically large Magnus forces. We eventually found a paper giving us a saturation model which limits the force produced at high spins, fixing the problem. In order to test the accuracy of our simulation, we took our best test run's real-life launch data and inputted its path and its potential error into the plot alongside our simulation's trajectory.
It is also very important that we consider the uncertainties involved in the experiment. The error bars are mainly due to wheels contacting randomly with the ball surface, causing inconsistent launching. Another reason is the motion blur of the ball in the videos, as we have limited budget and cannot purchase high-end, high-speed cameras to observe it more precisely. Another phenomenon we found when observing the spin axis was that since we drew large dots on the ball surface to count the spin rate, gyroscopic effect of the ball tends to occur in high spin conditions due to the mass of the ink, which changes the supposedly constant spin axis. Due to limited time of the project, its effect on the trajectory of the ball was not to be further investigated. Anyway, that's how curveball works, with beautiful physics behind. Thanks for watching.